Film Processing and Sensitometry, Chapter 20 and 21. Purpose of film processing: to accumulate enough black metallic silver at the sensitivity specs to yield a visible image. Film processing involves 4 steps: developing, fixing, washing, and drying. Developing. Visibility of silver at the latent image sites. It consists of these primary agents: reducing agent, activator, restrainer, preservative, hardener, and a solvent. Reducing agents provide free electrons to silver ions through gates of exposed sensitivity specs. With reduction and oxidation process, which reducing agents oxidized gives up an electron changed back to black metallic silver. This is a positive action. Sensitivity specs: only negative electrons, such as bromide and iodine, are exposed film. A large gate when more silver ions are deposited at the spec, which means a faster reduction of the internal silver atoms. Reminder of our, again, looking at that cubic lattice that we discussed in the chapter before, that the negative electrons are on the exterior and the positive are on the interior surfaces of that cubic lattice. Reducing agents neutralize positive silver ions. So again, let me say that. Reducing agents neutralize positive silver ions. So there's really 2 reducing agents, phenidone and hydroquinone, and they work together. So phenidone is the P developer, works quickly to produce shades of gray. Hydroquinone, or the Q developer, works slowly to produce black areas. And then you've got the super additive, and this is when the 2 are actually combined. So what you're looking at on this example or this curve, the P equals controls the high curve, and the H equals or controls the low curve. Used developer becomes oxidized, which reduces the strength. If not properly replenished, it changes color. First, it becomes a deep amber, next a brown, and then finally a rust red. Activator: typically sodium carbonate, added to developer to maintain its alkyne pH. Helps reducing agents get the silver halides. Swells gelatin, makes it easier to penetrate. Makes developer solution caustic, so you need rubber gloves and an apron should be worn. And neutralize spills with a fixer or dilute with water. Next would be restrainer. This is typically potassium bromide. Provides a distraction to overactive reducers. Prevents developer from acting on unexposed silver halide crystals. The preservative: the developer is easily oxidized by air. Sodium sulfite decreases this oxidation process. Additionally, careful tank design can reduce the developer's exposure to air. That's why you'll see like a tall, narrow tank seems to be better than like a low and wide. And your developer tank will actually be tall and narrow for that reason. No more than a 2-week solution or supply of solution should be held. Hardener: best way I can tell you to remember this is glutaraldehyde, so harden your glutes. It does control swelling of the gelatin, prevents abrasions during processing, maintains uniform film thickness. With low levels of hardener, it allows the gelatin to stick to the rollers, so this can cause a few problems. We end up with processor jams, or some type of artifact can be found on the film. It may present as moist, sticky films even after being dried. And then you'll know that you have a hardener issue. Too much hardener will harden the emulsion too soon, and that prevents chemical interactions from happening. So you end up trapping moisture into the actual gelatin itself. Solvent: solvent's always an easy one to remember for both the developer and the fixer. It is water. It should be filtered, 5 to 10 micrometer filter. In tropical areas, it should be treated for bacteria and fungi. Contamination: developer is impacted by contamination. 0.1% of fixer present in the developer will stop action of the reducers. It results in a gray, low contrast film. Developer is carried into the fixer tank routinely. Thus, developer does not contaminate fixer. So again, just a little bit of fixer will stop the production in the developer and ends up with low contrast films. Contamination. Splashing is one of the most common ways or common reasons for contamination. This can be avoided by using splash guards. When cleaning the processor, first the fixer tank should be filled, then second the developer tank should be cleaned. When shutting down the processor, the lid should be opened. It prevents fixer condensation from dripping into the developer tank. So condensation is just, again, that evaporation process. Because it is heated, that it will, if the lid stays on and not propped in the processor, it will evaporate, stick to the lid, and then drop down into the developer, which again can be a major issue. Fixing. Undeveloped silver halides must be removed from film. This consists of clearing agent, which is our primary agent this time, activator, preservative, hardener, and solvent. Again, developer does not act on the undeveloped by the restrainer. So test purposes, you really need to know the difference between the developer and the fixer and these agents that it's composed of and what each of the agents are. So the clearing agent, this is usually ammonia thisulfate. It bonds with unexposed silver halides, becomes ammonia thisilver sulfate. Films will appear milky if not properly cleared. So typical clearing time is between 15 to 20 seconds. The activator is acetic acid. It maintains an acidic pH, enhances function of clearing agent, neutralizes developer solution, and stops the action of the reducers. The preservative, this one is the same as developer. It is sodium sulfite. It removes silver from ammonia thisilver sulfite, so it allows the ammonia thisulfite to continue to remove the silver halides. Hardener, glutaraldehyde only works in alkaline, which means only going to work in the developer. So the hardener for the actual fixer is aluminum chloride, chlorium alum, or potassium alum. It serves the same purpose of the developer hardener. It's just maintaining the film thickness. Again, I mentioned solvent is the same for both. It's going to be filtered and treated water. Depletion. So fixer eventually becomes silver saturated. The clearing time gets longer and replenishment prevents depletion. So silver recovery removes silver from used fixer solution. And we'll talk about that a little bit more with silver recovery and the replenishment systems. Washing. Water removes as much of the chemistry as possible. So temperature should be 5 degrees Fahrenheit, 3 degrees Celsius, lower than the other solutions. If it's too cool, the emulsion will reticulate and the film will have a cracked appearance. If fixer is not washed from the film will become yellow, then brown with age. Proper washing requires agitation and enough time. Wash tanks are prone to algae and bacteria growth, so the tank should be drained when the processor is shut down. Drying. This is accomplished by forcing hot air over both sides of the film, and that's usually 120 to 150 degrees Fahrenheit, 43 to 65 degrees Celsius. It hardens the emulsion and seals the supercoat. Storage. Storage is usually stored at 70 degrees Fahrenheit and 60% humidity. Length of storage is dependent on the state law and institution. It's really usually between 5 to 7 years. Minor and legal cases are indefinite, and mammograms are also indefinite. Transport system. You need to know how to disassemble and assemble a processor. There are really 3 main subsystems that we will look at or discuss: the transport racks, the crossover networks, and the drive system. Transport racks. There are three series of rollers. They provide constant tension to move the film through each tank. Turnaround equipment at the bottom of each tank. You have a master roller, planetary rollers, and a guide shoes. The crossover networks. Similar to the turnaround equipment and transport racks, they turn the film at top and then turn it around, just kind of like it says there. Its misaligned guide shoes can scratch film. You also have a entrance roller, which starts the film. Film feeding always straight along the short axis, alternate sides to avoid excessive wear. If it's put in lengthwise, it calculates wrong, so you always put your film in crosswise. The drive system. This is a series of gears and mechanical devices, turn rollers, driven by a single motor. The speed of the motor determines the length of time for processing. A 2% change can affect the image quality. Squeegee crossover rollers. These remove excessive water. They can stick together with other film otherwise if all of that is not squeezed out. Hot air blown through the slotted tubes, and it shrinks and seals the film in one single pass. Replenishment system. This replaces chemicals as they are depleted. There are two types of replenishment: volume replenishment, which is for high volume, and flood replenishment, which we use for low volume. It's activated once it enters the entrance rollers. Developer starting and seasoning. The starter solution, acetic acid and potassium bromide, must be added to fresh developer chemistry. There's no bromide because no films have actually passed through the processor yet. So seasoning, adequate mixing of the developer chemistry is necessary and requires running the processor for 15 to 20 minutes prior to processing films. Replenishment rates: 4 to 5 milliliters of developer per inch of film and 6 to 8 milliliters of fixer per inch of film, but can vary depending on the manufacturer's conditions. Processor solution safety. Again, for test purposes, you might want to know that we are sanctioned through OSHA and the EPA, as well as MSDS. So we are dealing with hazardous materials, and with that being said, you should use protective eyewear and have some eye wash available within your dark room, and then you need to have the availability of rubber gloves and an apron. Circulation system. This stabilizes the temperature, agitates and mixes chemistry, and filters solutions. Constant mild agitation of the tanks is also required. The fixer is considered toxic and cannot be dumped into an open drain. The wash tank must have a constant flow of fresh water. Do not put into the actual sewer lines. So you're going to have within your dark room a separate drainage system. Temperature control system. This maintains all three solutions at compatible temperatures. Varies depending on the manufacturer used. So heat exchange is most common system. You have a thermostat to heat your developer. In a 90-second, the temperature is usually between 92 and 96. And in a 2-minute processor, the temperature is between 83 and 86. The developer tank is the most critical. A difference of 0.5 degrees will have a huge impact on the actual image. The darkroom. Lightproof lab used for loading and unloading cassettes and feeding into the processor. So we're going to discuss safe lights, the entrance, the pass box, and a plan. Safe lights. There's several different types that we're going to discuss. The Kodak's GPX filter is dark red. It has a low intensity of 7 to 15 watts. It needs to be at least 4 feet from your work area and a direct illumination possible with most films. The Kodak Raton Series 6B. This one is orange-brown and has an amber filter. It's safe for films sensitive to blue-violet light. So again, for test purposes, you might want to know the difference between the different types of safe lights. The LED is one of the more newer lights, safe lights that are available. So it is called a light emitting diode, which stands for LED. It has a high initial cost, but it is very long lasting. If there are too many safe lights, it can result in too much light intensity. So you do have to do a safe light test, which helps to determine the fogging on your films. Benches and flooring, these are usually going to be in light color to increase the light reflection in the room. It makes it easier to locate the film because, again, you're in total darkness except for a little bit of red light. So with white walls, white benches, white floors, it will help reflect that light so that you're able to visualize a little bit more in the actual darkroom itself. The darkroom entrance. Single door is equipped with a lock once inside. There is a double interlocking door. So just like it sounds, you can't open the second door until the first one opens. A revolving door, which is like the one that you see here, and then a light-proof maze. Look at your film bins always before actually opening your doors. Accidental exposure, it can be very costly. Pass boxes. You'll notice that one side it says exposed, and then there's an unexposed compartment. This allows cassettes to be passed to and from the darkroom. It prevents light from entering during the process. Plans. Processor feed tray into the darkroom. Other portions are all outside of the darkroom for maintenance. Pass box, film bin, loading bench, proximity to the feed tray. So it all needs to be really close to your processor for you to be able to work in a dark environment. And then you usually sometimes have a loading bench grounding as well. Communication system. So a lot of times you're going to need to speak to each other, so they'll have some type of system for communication, intercom, 2 separate vents, a white light and a safe light switch, ventilation, because again we're dealing with some harsh chemicals, humidification, and then also floor drains. Silver recovery systems. Again, Fixer is really valuable because it does consist and hold silver, which can be sold and processed for money. So there is a metallic replacement system, electrolytic, chemical precipitation, and resin. And film can be recycled and sold again for that silver aspect. This is all done after processing, and it is more valuable than actually before processing. Fixer dwell time is an important factor in the actual recovery period. Metallic replacement. Fixer acid breaks down the iron in the steel and displaces or replaces with silver. Iron gives up electron from the silver, and in low volume situations it needs a separate drain. Electrolytic. Pass current from cathode to anode through the fixer. Ionized silver attracts to cathode. It should not be used when the processor has not run for a long period of time, and it is used with moderate and high volume systems, and then it does need regular maintenance as well. Chemical precipitation. The chemicals break down and release electrons. It falls to the bottom of the tank, and then the toxic and explosive gases, this system is used for large volume hospitals or facilities. Resin is acid to form ions. Silver attracted to the resin forms a black metallic silver and then processed and then removed. There's several different types of monitoring these systems, which is like the penny test, test strips, or tailing unit. You can look through these case studies on your own, and we'll do that in class as well. Film sensitometry, Chapter 21. Sensitometry measures the response of film to the exposure and processing. So this is after the X-ray, the film is 2 times as sensitive. It's accomplished by exposing and processing a film, then evaluating the resulting densities. The purpose of sensitometry is evaluation and maintenance of exposure factor systems, evaluation of intensifying screens, and monitoring of processing equipment. The penetrometer or sensitometer are used to create a uniform set of densities on a film. The densitometer provides measurement of light transmitted through film and measures the optical density. So penetrometer we will discuss a little bit further here. This is AKA known as a step wedge. It's used to monitor X-ray equipment, also used to monitor film screen combinations, not recommended for processor monitoring. So again, not for the processor itself. Actually take the image at first, and you actually take a picture of this equipment on a cassette. Most of the time you try for a spot on the same spot on the film all the time. Sensitometer, this is an electronic source, so you don't actually have to take an image of it on a film like you do with your equipment with the penetrometer. So it uses a controlled light source, and it provides the same amount of light each time it's triggered. It should not be touched because hands leave an oil that can actually interfere with the light process, but it's the same thing. You want to actually use it in the same place on your film every time. It's available in 11 or 21-step version. The 11-step version increases density by a factor of 2 for each step. The 21-step version increases density by a factor of square root of 2, which is 1.41 for each step. This is actually good for processor quality control monitoring. The densitometer is the equipment to read both the penetrometer and the sensitometer. It has a uniform light source and an optical sensor. The calibration control allows for easy calibration. It provides a readout of the amount of blackening on the film. So again, densitometer provides a readout of the amount of blackening on the film. Each time you set it to 0 to prepare for a reading, the readings are accomplished by comparing the amount of light emitted by the light source with the amount of light transmitted through the film. Optical density numbers. There is a formula, which is optical density equals log 10 over IO over IT, which IT is intensity of transmitted light and IO is intensity of incident light, and then log 10 is the density of opacity. If 100% of the light is transmitted through the film, it has an optical density of 0. If none is transmitted through the film, you have an optical density of 4. Opacity is ability of a film to stop light transmission. So the formula is IO, which again, intensity of light transmitted, divided by IT, which is intensity of light of transmitted light. You do not need to memorize the table 21-1, but it does go a little bit further into opacity. The D log E curve. It describes relationship between density and exposure. So again, D log E is density log exposure. This is done through sensitometry, aka the sensitometric curve, characteristic curve, Herter and Dryford or H&D curve, all represent the D log E curve, so those are all known as the same. Sensitometry's roots lie in analysis of photographic film, and that all started in the 1860s. The sensitometric curve plots optic density versus LRE, which is the log relative exposure, and allows large range of exposure displayed in a few numbers. And so when you're looking over here to the right, you see a diagram of the actual curve. A is the base plus fog, B is the toe, C is the straight line portion, D is the shoulder, and E becomes the D max. And we'll talk about the parts of the curve a little bit more as we go through this lecture. Densitometer. Again, these are read on a scale of 0 to 4. 0 meaning, again, that all the light is transmitted, and 4 means no light is transmitted through the film. Typical diagnostic densities range between 0.25 to 2.5. So when we actually look at the parts or the actual sensitometric curve or the D log E curve, you'll notice it starts normally between 0.25 and ends at 2.5 for the diagnostic portions. Parts of the curve. The base plus fog, density is at no exposure. Again, your film has different types of dyes in it that we've already discussed, and some basic fog from the manufacturers. So the measurement that you first take is 0 exposure and will be approximately that above 0. The D minimum, or the toe, is where the density becomes light, and then the straight line portion is the diagnostic portion. It's used to demonstrate the relationship to film exposure versus the density transmitted. The shoulder up to the D max is where the density becomes dark. Film properties. Base density is inherent in a piece of film due to dyes, etc. Value is usually 0.1 optical density. Fog density is inadvertent exposure during storage, handling, etc. So fog density should not exceed 0.2. So heat, chemical, fumes, light, and radiation, most will be caused by hypersensitivity of developer caused by high temperatures. Base plus fog. Cannot separate base and fog density measurements, so it's always going to be a measurement together. Typical range of optical density for base plus fog is 0.18 to 0.23 and should never exceed the 0.25. The D, minimum, or TOW, is controlled by the phenidone. It's fast-acting, reducing agent in the developer, produces gray tones on the film. Straight line portion. This is also called the gamma portion. It's the area of the curve between the toe and the shoulder and contains the range of useful densities, which again is the diagnostic information. It's typically between 0.25 to 2.5 or 3.0. It's straight because the film is reaching its linear fashion to the actual exposure. The shoulder is controlled by the hydroquinone. Again, important test information here is the toe is controlled by phenidone and the shoulder is controlled by the hydroquinone. It's slow-acting reducing agent in the developer, produces blacks in the image. The Dmax, maximum density able to be recorded on the film. Silver halides are full of silver atoms and cannot accept any more. Again, Dmax, silver halides are full of silver atoms and cannot accept any more. Reversal or solarization. So this is really a duplication. Film has been solarized, and we discussed that looking at film a couple weeks ago. So once a film has been exposed to Dmax, it will begin to lose density, and after further exposure, less density because silver atoms attracted to the speck will be ionized again, changing their charge and causing them to be repelled. Film characteristics, and we'll discuss each of these individually as we go through here. Resolution, speed, contrast, and latitude. Resolution, the ability to accurately image an object. Again, resolution is known as detail, sharpness, definition, resolving power. So again, all of those are all still representing resolution. It's measured by the ability to see line pairs or line pairs per millimeter. It's inversely related to size of the silver halide crystals. The smaller the crystal, the greater the resolution. Smaller crystals will darken small areas and large areas. Think silver halide, sometimes called grains or graininess, which is poor resolution. Speed. Speed is known as the amount of density a film produces for a given exposure. Ability of an IR to respond to low exposure measures is sensitivity or speed. The speed index is specified by 1.0 plus the base plus fog. So in this image, the film A speed point is going to be faster than film B. So the faster film will have a curve closest to the y-axis of a graph. So again, this might be important information to know for test purposes. Film sensitivity is affected by the size of silver halide crystals, the number of sensitivity specks, and the thickness of the emulsion. All of the above are directly related to film speed. It is affected by processing as well. So the chart you're looking at here is developer immersion time. So immersion time will affect the speed. Solution temperature, mostly affected by the developer solution temperature, and chemical activity. So here's some more graphs. Developer temperature on film is the next one there that you see. And then on your right, this one is looking at the average gradient densities and fog and speed. So this is how manufacturers arrive at the time and temperature that is going to be required for each set of film. Increased developer activity increases density. If not properly formed, insufficient of excess restrainer or over replenishment. Contrast. Again, the definition of contrast is the difference between adjacent densities. Contrast is controlled by the hydroquinone. Hydroquinone establishes the shoulder, thus it affects the slope of the straight line portion of the curve. Film contrast and curve. Film contrast is defined by the straight line portion of the characteristic curve, gamma slope, or again called straight line. As the line becomes more vertical, the contrast gets higher. So again, as the straight line becomes more vertical, the contrast gets higher. Average gradient. This is the straight line portion. It's used to identify contrast of a film by manufacturers. Slope of the line that is drawn between 0.25 above the base and fog density. Average gradient. The slope of the line that is drawn between and 2.0 above base and fog density. Higher the average gradient, the higher the contrast, and this affects and changes to contrast. Gradient points are sometimes known by their location. Gradient points are also sometimes known by their location. Latitude. The lower the slope, the more horizontal the line, the wider the latitude. Latitude and contrast are inversely related. Decreased latitude, increased contrast. Latitude is the range of exposures that will produce diagnostic densities. Low scale of contrast in film, you have more latitude and more of a margin of error is higher. Again, you can go through the case studies on your own here. Some great helpful hints in studying would be table 21-2 and 21-3. The slower the speed, the higher the patient dose, the faster the lower.